Okay, good morning, you guys. Happy Monday. This is our last chapter. I just kind of wanted to lay it out for you. This is chapter 9 in our book. Um, it's called Discrete Mathematics. It has 4 sections, so we're going to do 4 sections this week, and then we're going to test next week, and then we're going to maybe talk about what our final week looks like after that, but we're pretty much done. Yay for that. Okay, so section 1, you can see I listed the 4 sections for you. Section 1 is basic combinations, basically, our combinatorics. Let's talk about permutation and combinations in this section. It's pretty, very basic on that subject, so if you've done it before, maybe you did it in algebra sometime. I can't remember when you might have seen this. If not, it'll be good for you to have at least seen it before, so something that you should have seen at some point. All right, so we're going to talk about just like counting something. Okay, so in how many ways can you arrange 3 distinguishable objects? Okay, so you might not use a formula or something like that for this. You might actually just try to like count it out. Or sometimes they have like if you've seen this before, they have like a tree diagram where you have like, let's say 3 distinguishable objects are A, B, and C. So we have A, B, and C. Okay, and then you can do like this would be B, C. You'd do like a little tree here. And then you'd kind of count them out to see how many you have. And you can see how many leaves you have on your tree here. There's 6, but you could also, like I said, just list them out. You could go, oh, I'm going to do A, B, C. That's the first one there. I'm going to do A, C, B. B, A, oh, this has to be B, A, C. B, C, A. That's these. I'm going in order of these. You can look at them. C, A, B. And C, B, A. And, there's 6. So there's 6 ways to arrange 3 distinguishable objects. Okay, so, that's called counting. And of course, you wouldn't want to do that when it gets larger. So, like, let's say we had 5. Making a tree diagram or sitting out and counting a bunch of them can be kind of tedious, right? So, that's where we get into some of this stuff. Okay, so we get into the multiplication principle. That's what we kind of did on the one before. We did, there was 3 levels. Let me go back real quick. There was 3 of these times 2, right? Because that's how many it made. So that's kind of how we did the counting there. All right, so that's what they call the multiplication principle. Okay, so let's use it here for an example. A license plate consists of the alphabet followed. I messed up here. I didn't write this. A license plate consists of 3, I didn't write that down, 3 letters of the alphabet. There we go, that's better. Followed by 3 numerical digits, 0 through 9. Find the number of different license plates that could be formed. Okay, so the first thing we want to do is there's no restrictions on letters or digits. Like that means, you could have A, and then 1, 1, 1 if you needed to. Okay, so like let's make blanks here. So we've got 1, 2, 3. That's our alphabet. 1, 2, 3. That's our numbers. Okay, so we fill in the first blank and we would do 26. Second blank, 26, right? And then 26, there's 26 letters of the alphabet. This was our alpha. And this is our numbers. Okay, and there was 0 to 9. That's 10 numbers, not 9. This would be 10, 10, 10. And so we would multiply all these numbers together. So you'd have 26 times 26 times 26 times 10 times 10 times 10. And that would be a really big number. That's how many ways or how many possible license plates there are if you have no restrictions, okay? So then if you have restrictions, let's talk about that. No letter or digit can be repeated. So we're going to do the same thing. So those are my alphabet. These are my numbers. Okay, so if I use all the letters, that's 26, but I'm taking away the one letter that I used. So let's say I used A. Well, then in the next spot, all 26 is not available, right? We have to take away 1, so 25. And then again, if I used A and B, let's say, then I have 2 fewer than the entire alphabet, so that's 24. Okay? And then the same with the numbers. If 10, 9, 8. And then we multiply all these together, and we get a little bit less. As you can imagine, if you have a little bit, you have some restrictions. Okay, and so that's how many possible license plates there are when no letters can be repeated. Okay, all right, so that's kind of the counting way of doing it. And I'm going to come back to counting at the end too and do a couple more examples. But let's get into permutations and combinations. So first we're going to start with permutations. This has to do with counting too, but it's just more of a formula way to do it versus sitting and multiplying everything out. Okay, so it's to count the number of ways that a set of n objects can be arranged in order. So I highlighted the word in order. We need to remember permutation, order matters. When we get to combinations, it does not matter. Combinations, order does not matter. Okay, so permutations, if you write down anything about permutations besides the formula that we're going to get to in a minute, order matters. Okay, so all right, so let's get to the example. So I wrote down the example. It says count the number of 9-letter words that can be formed using the letter in each word. Okay, so how many letters does it have? It should have said 9, but I'm going to count to make sure. Okay, so this would be 9 letters. Okay, so none of these, let's think about what we just did before. I'm going to do this out in the counting way, and then I'm going to show you. Let's see if I made sure. 1, 2, 3, 4, 5, 6, 7, 8. Maybe one more. So, okay, so we would rearrange these in any way, but once I used 1, so I have 9 letters to choose from, and then I have 8, 7, 6, 5, 4, 3, 2, 1. And you would multiply that. There's actually a word for this. It's called 9 factorial. Okay? And that is in your calculator. Pause for a second. I'm going to run get my calculator. Okay, sorry, I had to run and get my calculator, but I didn't want to start over. Okay, so there we will be using factorial a lot. So on your calculator, no matter what calculator you have, it's under math. Let me find it. And you go over, so I'm gonna draw this out since you're listening. So it's math, and then you have to scroll over, because this is what we're doing right now, probability, P-R-O-B. And there you'll see number 4. It's an exclamation mark, but we call it a factorial. That's what it's called, a factorial. Okay, so we will be using that a lot. Okay, so if I was doing this problem, now that you know, I wouldn't do any of this writing out business. Okay, let me erase this for a second. So let's say we are starting from the beginning here. Okay, and I'm going to ask you again, 9-letter words. Here's the important part. None of the letters are repeating. Okay, if they're repeating, it's a little bit different. So we'd have 9 factorial, which is 9 times 8 times 7 times 6. But I'm going to do it in my calculator. So 9, go to math, scroll over. Go down to 4. 9 factorial is 362880. Okay, so that is the answer for this word dragonfly. Okay, let's try another one. So B, we've got butterfly. Okay, there are also 9 of these, as there's 9 letters, except the 2 T's do not result in a new word. So like you're interchanging them, but they don't have a new word when you're interchanging the same letter. Okay, so here's how we overcorrect. So right now we have this number right here, but we need to overcorrect because of these 2 T's right here. Okay, so we overcorrect by dividing, so 9 factorial, and then we have these 2 repeating letters here. Okay, so this would be, and I would just put it in your calculator, but if you wanted to see a visual of what this looks like written out, this is 2 times 1. So this, is what you're multiplying. 9, 8, 7, 6, 5, 4, 3. 2 and 1 cancel. Okay, but if you just do it in your calculator, you'll get 181, 440. Okay, now, the formula says, you should have n factorial, so the number of letters, and then the number of letters for each, like the number for each letter. So I'm going to kind of show you what you get the point. Okay, so like B, how many B's are there? There's 1, so 1 factorial. How many U's? 1 factorial. How many T's? Well, there's 2 factorial. How many E's? 1 factorial. And so you keep going, and this number has to add up to whatever this is, which was 9. So this needs to add up to 9. But here's the deal. We don't write 1 factorial because 1 factorial is literally just 1. So we leave out the 1 factorials, but we do want to include in anything that's a multiple or that wouldn't be just 1. Okay, so that's kind of what they call the distinguishable, I'll just give you the word, distinguishable permutation. Okay, all right, so let's do C. You can see here 9 letters again, so we know it's this, except for the fact we've got some repeating letters here. Okay, we've got 1, 2, 3 B's. Okay, I'm going to kind of put a line through them. Okay, so we got to factor that in. And then we also have, it looks like 1, 2, 3 E's. Okay, now if you're really writing this in a way that, the formula says, you could do, there's 1 U, there's 1 M, there's 1 L, and then this number right here took into account all the letters. So this was the B, this was the E, this was the U, and this is the M, and this is L. Those are all the different letters. But again, we don't write the ones because it's kind of silly. It's like writing 1 times 3, which we all know is 3. So we just don't write the ones. But we would write 9 factorial, 3 factorial, and 3 factorial. Okay? And that's going to give us 10,080 different ways. Okay? So a lot fewer because we have like some repeating letters in Bumblebee. Okay, so we had to count it twice. We had to do twice an overcorrection there because we had 2 letters that repeated. All right, so hopefully that's, you'll see words, and that's what you do with words. If they ask you about letters, words, how many different ways you can arrange, this is what you're doing. Okay, all right, so let's get into the permutation counting formula, because you know that they try to make things easier by putting it in a formula. So I already wrote it down so I could save some time here. I'm trying to talk not as long. Okay, so this is important. This is the permutation counting formula. There'll be another one for a combination. Okay, and it's just a formula. Okay, so what the N is in objects, and the R. Okay, so there's total in objects, and R is taken at that time. So the number of permutations of n objects taken R at a time is denoted like this. Okay, so this is a formula, and I'm going to show you how to use a formula. All right, so here's some without any words. You don't have anything like that. You know, no, how do I do this? No words, no pizza, no nothing. Okay, so here's the first one. You've got a permutation of 6 objects taken 4 at a time. Okay, so here's how you write that. So it'd be 6 factorial divided by, and this would be 6 minus 4 factorial, which is 6 factorial divided by 2 factorial. Okay, and remember, if you're just kind of multiplying it out, 6 times 4 times 3 times 2 times 1 over 2 times 1. So guess what? The 2 times 1's canceled out. So literally it's just 6 times 5 times 4 times 3, which gives you 360. Can you do this in your calculator? You can. I'm just trying to give you a visual of what you're doing exactly so you'll know. Okay, so here's another one. So we have, I'm going to kind of shortcut it because I think you kind of all can do the math there. So 11 factorial over 11 minus 3, which would be 7 factorial. So this is going to be 11 times 10 times 9. Shoot, let me try that math again. 11 minus 3 is 8 factorial. So sorry, it's a Monday. You know what happens. So I would do 11 times 10 times 9. That's it. And that's going to give me 990. Okay. Now, I find this interesting. I'm going to show you. So, see this number 4 right here? How many numbers did I actually multiply together if I multiply this out? 6 times 5 times 4 times 3. That's 4 numbers. How many, and this is why I knew I did my math wrong, because I know how many numbers I need to have here. 11 times 10 times 9. And notice I was writing a multiplication sign, and I was like, that doesn't make sense. So I knew I had done my math wrong right here. This should be 8, not 7. 10 minus 3 is 7. 11 minus 3 is 8. And I knew there would be 3 numbers right here, because in the rest, 8 through 1 would be eliminated by this bottom part. Okay, so I don't know if you find that interesting or not, but I like to look at things like that. And again, it helped me find my mistake because I knew how many numbers I was going to write here. Okay, now let's do C. Okay, so we have N objects and 3 blanks to fill. Okay, so this would just be N times N minus 1 times N minus 3. Because remember, we just decided this was 3 numbers. So there's my first number, my second number, my third number, just like this one, just because there's a 3 there. Okay, so for example, I'll do another one. So if I did P in 5, I'm going to be here for a minute, but I'd do N minus 1, N minus 2, N minus 3, 1, 2, 3, 4, and N minus 4, because that'd be 1 number, 2, 3, 4, 5, because of that. Remember I talked about how this is, how we have 4 numbers here. Okay. All right, hopefully that makes sense. If not, let me know. Oh, let me know, and I will Zoom with you, and we can try to go over it again. Okay, so now you know how to use the permutation. Let's now apply it to a problem. So 16 actors answer a casting call to try out for the roles as dwarfs in the production Snow White and the 7 Dwarfs. How many different ways can the director fill the 7 roles? Okay, so order matters here because we got different dwarfs, right? So if it's not just filling the spots, you are actually filling a specific role, okay? So order matters, okay? And so we're going to write it like this. Oops, sorry. We're going to write it like we just learned. So the P, we know it's permutation because order matters. We have 16 and we have 7 spots to fill. So this is N, this is R. Okay. So 16 actors and 7 blanks to be filled. Okay, and then we just do what you normally do and use your calculator. 16 factorial over 9 factorial, and you find that it is 5, 7. That's how many ways they could fill those spots. Okay, so I'm going to do it in my calculator right now because I want to just double check myself. Yep, okay, there you go. Okay, so that's how you use the permutation counting formula. All right, so let's move on to combinations. Again, I wrote out these things so I didn't have to write as I did. So combinations, here's what you need to do. No, it's the same exact thing. You've got so many, let's say people, I'll just use people, or so many things, and you're filling so many blanks. Okay, but here order does not matter. Okay, so that's the difference between combinations and permutations. And of course, we'll get into, oh, I think I'm going to, okay, I'll need to erase and show you the combination counting formula here in just a second. But we're gonna try to figure out which ones are combinations or permutations below, because those are some of your questions on your homework. Is you have to decide, is it a combination or is it a permutation? Remember, permutation, order matters. Combination, or unordered or order does not matter. Okay, so let's look at this. Example A president, vice president, and secretary chosen from a 25-member club. You have to decide, does order matter here or does order not matter here? Okay, and I'm going to tell you, let you think about it for a second. Order matters because it matters who gets to the office. Okay, so order matters. This is a permutation. Okay, order matters. Okay. B, a cook chooses 5 potatoes from a bag of 12 potatoes to make a potato salad. I didn't write potato there because I didn't have enough room, but a cook chooses 5 potatoes from a bag of 12 potatoes to make a salad. Okay, so think about it. Does order matter here or does it not matter here? Okay, order does not matter. Doesn't matter which 5 potatoes, doesn't matter what order they go in. So here we have a combination. Okay, all right, last one. Let's see if you can get it. A teacher makes a seating chart for 22 students in a classroom with 30 desks. Okay, does order matter or does not order do not matter? That did not make sense. Okay, a teacher makes a seating chart for 22 students in a classroom with 30 desks. Okay. Order matters because if you put students in different desks, then you have a whole new seating chart. Okay, so a different ordering of students in the same seats results in a different seating chart. So you move one student and you got a whole new seating chart. Okay, so order matters here. So this is a permutation. Okay. All right, so I am going to kind of show you how to go back and write these as permutations. So this was a permutation, and we had 25 members with 3 slots to fill. Okay, this was a combination, and we write it the same way. I'm going to give you the formula in just a minute to use. This formula is not exactly the same, but we had 12 potatoes, and we were taking out 5. And then this was a permutation, and we had 30 seats, but we were writing, 22 we only had 22 students to put in the desks. okay? And those, you would put them in your calculator and get the answers. Okay, I haven't given you this formula yet. I'm about to do that. Okay, so I'm going to erase this really quick because I already made an example on the next page and forgot this very important part of giving you the formula. All right, so let's see what I got. This is going to drive people nuts. So I'm going to try to get every little dot. Okay, I think I got it. All right, so let's write out the combination counting formula. Remember, we had the permutation, so this is the combination where order doesn't matter. So it looks like this. Oh, I'm going to redo that. Okay, so it's similar, but not exactly the same. Okay, we also need to note these things, just in case they try to trick you with one that doesn't meet the rules here. I'll write these down. Okay, so this is the formula. Okay, the number of combinations of n objects taken at r time is denoted just like this, okay, and is given by this formula right here. All right, so sometimes I do want to note the different books write a different way. Sometimes you'll see it written like this. Okay, it's the same thing as what we got going on here. And sometimes also you'll see it written like this. Okay, we might see this in the next section, so I wanted you to, combinations are the only way you write them like this. Now, permutations, you can have this way to write it, but you can only write combinations like that. Okay, and that's read N choose R, N choose R, N choose R. Okay, N choose R, just in case we want to read it like that. Okay. All right, so we might use that in the next section, so I wanted you to make sure you had seen that. Okay, so let's look at this next question. In the Miss America pageant, 51 contestants must be narrowed down to 10 finalists. How many ways can the 10 finalists be chosen? Now, notice that order doesn't matter. We're just picking 10 people. Now, if they said top 10, so we have first, second place, third place, fourth place, fifth place, that would mean order matters. But just picking 10 finalists, there is no order. So order does not matter here. So we're going to use a combination. Okay, so we write it like this. C, oh, that's a terrible C. C, and then we have 51, and we're picking 10. Okay, so the formula would be 51 factorial over 10 factorial, 41 factorial. Okay, so now I am going to tell you that there is also in that math probability, if you look at the second and the third one down, you have an N and a C button. I would probably recommend using it because you're going to have big numbers like this one. And you have to know what this means. Okay, you guys, you got to know about scientific notation at this point in your career of math and science. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So mine says, and yours would too, you have to realize that that is not an appropriate answer that you can put into the Math Excel. This doesn't make sense, okay? E to the 10 means I need to move this over 10 decimal places, okay? So that's 2, 7, 7, 7, 7, 1, 1, 8, 7, 0, because I'd have to go, there's 9 numbers here. Okay, so please make sure you know how to use scientific notation. Okay, when I did it, this is what my calculator produced. Every calculator is different. Yours might not, but that's what mine did because I didn't have enough numbers to put there. So do not enter it like this. This would not make sense, 1.27 for an answer. Okay? All right, let's do one more. Let's do one more combination here. So a lotto requires winners to pick 6 numbers between 1 and 46. The order in which you select them does not matter, so we already know we're going to use combination. They told you that in the sentence. How many different lottery tickets are possible? So this is easy. So C, 46, and we have 6 spots to choose from. So again, I just put it in my calculator, and I get 9,366,819. That's how many possible lottery tickets you can give. That's huge. That's one of the lottery's heart. Okay, pretty easy so far. All right, so the last example I want to talk about is not necessarily combination permutation. It's like it's the pizza topping problem, or the different ice creams. You've probably seen them before. Okay, so I'm going to kind of show you how to do those. All right, so pizza topping problem. I kind of summarized this because I got tired of writing, but there's a pizzeria. It offers 10 different toppings, and they list all the toppings. You got mushroom, you got bacon, you got green pepper, you got onion, you got blah, blah, blah. It doesn't really matter what the toppings are, there's 10. Okay, how many different pizzas can be ordered if we choose 3 toppings? Okay, so this would be a combination because you wouldn't care the order. You just have 3 toppings that you're choosing from, and you're filling the blanks for 3. It's kind of like the Miss America. We had 51 contestants. We're picking 10. So right now we've got 10 different toppings. We're picking 3. Okay, so it'd be a combination. Okay, oh, bear with me here. Okay, and I'm picking 3. Okay, so if I do the math in the calculator, I get 120 different types of pizza for 3 different toppings. Okay. All right. B, a little bit more complicated. If we can choose any number of toppings, so you can choose 0 or you can choose 10 type of toppings. Okay. So what you could do is you have this. Okay. And R would be anywhere. R would be 0, 1, 2, 3, all the way up to 10. And you could do each one of these. This would be, and you would add them all together. Okay, and that might take a minute. There's no really quick way to do it here, but you get the point, and you would go all the way to 10, which would be 1. By the way, oh, shoot. This would be 1 if you have 10 and 10, okay? Because there's only one type of pizza you can make with all 10 toppings. That makes sense, right? And so that's the way you would do it using the combinations, is that you would sit and add those up, okay? But there's also an easier way to do this. All right, I'm going to show you. That works. This way works. But there's also an easier way. Okay, so if you lay out the 10 toppings, let's say, all 10, okay, I'm a visual person, so I'm going to visually show you kind of how this works. So if I lay out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's say this is mushrooms, and this is onions, and this is sausage, and so on and so forth. If I just wanted these, if I wanted mushrooms, onion, and sausage, I would say yes to this, yes to this, yes to this, and then no to the rest. Does everybody agree? Okay, so what are our 2 choices here? Our 2 choices in the blank are yes or no, right? Does everybody agree? The 2 choices are yes and no. So essentially, I only have 2 choices for mushroom, 2 choices for onion, so on and so forth. This goes back to the counting thing that we did kind of at the beginning. So this would be 2 to the 10 power. If you think of it as 1, 2, 3, 4. If I wrote how many I'm supposed to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did. So 2 to the 10 power would be 1024. So that's how many different pizzas, which would be the same way if you did it the other way. This just makes it a little bit easier in the counting. Okay, this is just a counting one. All right, I'm going to do one more of the counting one from your homework, if I can open it. Okay, this is another counting problem, and towards the end, this is like number 18, it gets to these counting ones where you can just do them by how I did that last problem. Okay, so a multiple choice test. So multiple choice test with 6 questions. Okay, and each question has 3 possible answers. Okay, so think about that. You got six questions. 1, 2, 3, 4, 5, 6. What are the possible answer for each one of these? Well, you have 3 to choose from here. 3, 3, 3. And so here you are doing 3 times 3 times 3, 3 to the 6th power, which would be 729. So that's another counting one that you have to think about. Okay, so just wanted to give you a problem from your homework. Again, it's hard to do every single homework problem, but hopefully you can relate some of these. And remember, when order matters and order doesn't matter, that would be important. Okay? All right, so let me know if you have any questions. Screenshot it, send it to me. I'll work it out or help you work it out. I can Zoom with you and we can go over some problems. I just don't want to take up too much of your time going over every single type of problem you have. Hopefully this will help. Good luck, and I love you guys.